Hello, my name is Kobe Wordlaw, and this is Lab 3. During this lab, we'll use a magnetometer to measure the distance dependence of the magnetic field due to a small bar magnet and compare your measurements to the distance dependence predicted by the equations from the on and off axis magnetic fields derived from the Biot-Savart law. For this lab, you're going to need a magnetometer app. These are 3 apps recommended by my professor. I myself use the middle one, Firefox, because you can easily distribute um, the magnetometer X value, the Y value, and the Z value, as well as the net value, which is represented as absolute. Also, the units are already in microteslas. So once you download the app, you need to calibrate it and make sure that your phone is facing magnetic north. To do this, all you have to do is turn the app on, make sure it's playing, and turn it to where the X value gets as close to 0 as possible while your phone is laying down flat on the table. Once you do that, you'll be able to get the BNet value, and you can tell that it's as close to 0 if your BNet is close to the magnetic field at your location. So my latitude and longitude gave me a net value of 48.83 microteslas, and that is what my BNet was close to. So I knew that my BX was as close to 0 as possible. Next, we're going to need to find the magnetometer chip. I use the bar magnet, a meter stick, and the magnetometer app as well as tape. So to set this up, you're going to set the meter stick down on the table and put the magnet laying parallel to the meter stick. Then you're going to put your phone close to that bar magnet on the meter stick and move it up and down. As you move it up and down, you're going to be looking for the max Y value. When you get that max Y value, that is going to be where the magnetometer chip is. So you're going to put the tape along that line. Then you're going to turn your phone 90 degrees, and you're going to move it up and down again. And you're going to look for the max X value. When you get that max X value, you'll put the tape down where that aligns with the bar magnet. And where those two tapes cross is going to be where your magnetometer chip is, and you're going to need to know that for when you're getting measurements in the future of this lab. So next on the list is where we started gathering measurements and inputting them into our Excel file. To start, we wanted to find where our BX value would be 2 e to the negative 5 teslas. When we did this, we had to make sure that our phone was still on that axis where we found BX equals 0. So true north. And we want to make sure that it's always facing in that direction so we don't move it and mess up the calibrations, and that our measurements stay accurate throughout the lab. So we wanted to take 3 measurements of when our BX is equal to 2 to the negative 5 microteslas and get that distance measured from where we found our chip in our phone to the magnet. So my average distance for that ended up being 2.87 to the negative 1 meters. Then we wanted to repeat this for 3 more BX values, which was 7 to the negative 5, 1.2 to the negative 4, 1.7 to the negative 4, and 2.2 to the negative 4. Once we got the average distance for all of those, we were able to graph our ln BX versus our ln of R. So from our graph, we were able to pull the equation y equals negative 2.6128x minus 14.051. These values are very important. Our n value that we had to find in our original equation is equal to the slope of this y equation. So our n is equal to negative 2.6128. And our ln of k from that equation is equal to the intercept of this y equation listed, which is negative 14.051. From this k value, we were able to find our magnetic dipole moment. And this is from doing algebra. So we know that k is equal to mu naught over 4 pi times 2 mu. Then we would do a little bit of algebra, and we separate u to get u equals k over 2 times mu naught over 4 pi. I plug in my values, and I got 3.9509, which I will need for my code. So this is the code where we develop a visual representation for the magnetic field of this bar magnet. So if you look at the bottom right corner, lines 31 through 36, this is where I input the very long equations for finding the magnetic field, which is mu naught over 4 pi times 1 over r cubed times 3 times mu times r hat minus mu. It's a mouthful. But in the code is very condensed, and this is basically where a simplified version where I can input an observation location and a mu to get an answer. So between lines 53 and 91, this is where I am creating the arrows to visually show what is happening. I wanted to make different locations, basically showing 2 on axis and 4 perpendicular to the axis, which you can see from line 53 to 58. And by doing this, I kind of just created one and then made the negative version of that to kind of make it simpler. Line 64 through 71, this is where I made the 2 on-axis ones, and line 76 through 91 is where I made the 4 perpendicular ones. The 2 on-axis ones are orange, and the perpendicular ones are going to be cyan, which you'll see in the rendered version later. And then on the right side of my PowerPoint is lines 100 through 116, which is basically the second half of this experiment, which was seeing the correlation of my 45 degrees data and comparing it to this code. So we'll get to that one later also. So this is where I compare my data for 45 degrees to the coding. One thing I want to point out is where it says BY corrected. We needed to get the data for the BY of the bar magnet and subtract the magnetic field from the Earth, because we only want that the bar magnet. The data that is given on our phone is the bar magnet plus the magnetic field of the Earth. And to single out that bar magnet measurement, we need to subtract the one from the Earth. So that is where BY corrected is stating just strictly that bar magnet magnetic field. Next is the B net at a distance D. So the values are not far off. It's off by like maybe 3 or 4 Teslas. So as you see, the average is 4.951 times 10 to the negative 5 Teslas, and from the code, when calculated, it comes out to be 1.844 times 10 to negative 5 Teslas, and it's off because of different things. So it could be electronics near my phone, other magnets that I don't see, like metals and stuff like that. And it could also be because not properly keeping my phone secure and to not turning it and keeping it on the right axis. So I'm getting like a bunch of false measurements and stuff like that. So some questions. Number one is, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So if I wouldn't have compensated for magnetic north, um, our measurements will be very inaccurate because when I don't compensate for magnetic north, my values are going to be very skewed, and I won't be able to tell like have an accurate depiction of where it is on the x value, where it is on the y value. So it's just going to be a bunch of false information. What if the stick were two? What if I were to stick two identical magnets together into N and run the experiment again? How would I expect my measurements to differ? So I believe if I were to stick two magnets together, um, my results would be almost two times the value because I have two magnets that are exactly the same, giving off a magnetic field that is two times greater, basically. And that is it. Thank you.